So as people are returning to their computers, I will start to initiate the second part of this webinar, or the final part, which is a session about material understanding. And this session is more of a deep dive. It's called Material Understanding and the Recycling Potential of Plastics. So it will touch upon many of the same areas that we have already been through, but with a more material perspective. So we look at it from different materials and do a deep dive into some of the research done in what actually matters for recycling. So of course, this touches upon the same issues that we've talked about already, that plastics are, of course, indispensable in modern products, and also they span from everything from medical devices to everyday consumer goods. And their diversity is also a necessity. So the huge variety of polymers required for different applications is, of course, necessary, but also is part of why it's challenging to recycle. So as we also touched upon earlier, why do you need so many different plastics? Sometimes you could simplify it a bit, but of course, different products have very different requirements in terms of, for example, strength or weight or durability, appearance, safety, you name it. And for that, it's fantastic to have a product like different plastics that you can play around with to make the best possible products. But of course, it makes recycling solutions not very straightforward. So we take a deeper dive into these complexities, not just in general terms, but as I said, from a more material understanding perspective, trying to look at individual types of plastic on the molecular scale and what actually matters to the relation between not only composition, but actually structure into properties, and how that relates to specific cases, use cases that we have in some products. We want to really highlight that it's not really a one-size-fits-all. I think we all know that here now after the first session. But of course, we have lots of great solutions to many problems, but you always have to ask the question, what is right in this particular example? So we need to do that to have meaningful progress in circularity of thermoplastic recycling. And this fundamental understanding is part of it. It's like Lena showed us in the beginning, there are many different active aspects to look at. And one of the aspects is really the deep dive. And that's what we're going to do now. So what can you expect? We have looked into, in this session, specifically 3 types of plastic that we really want to look at deeper. So first we'll look into polyamide, and then ABS, and then polypropylene, and relate them to some case studies where this material knowledge is essential to understand what the issues really are for that particular type of plastic. Right, so whether you're new to the field or deeply involved in materials and production, we really want you to engage, so please ask questions in the Q&A, just like we did earlier, to make the discussion as relevant as possible. But we hope you leave the session with a clearer understanding of why polymer diversity is very complex, but also why it is needed. We also hope you leave with some new insights on the technical and strategic hurdles that we face, and where new innovative solutions are emerging, but also a sense of what kind of collaborations are actually needed and knowledge exchanges are needed to drive some change in a more circular future. Right, so let's get on with it. We have collected some of the core insights through some nice videos from our panel that will also have a discussion later. We will start off by looking at some actual products and some of the particular difficulties or challenges in actually a specific project. We'll start by showing you a video of Søren Kristiansen, who's also here, telling about some challenges in the Legos.
Hi, I'm Søren Kristiansen. I'm from the Lego Group. I will tell you shortly about the challenges there are for recycling of plastics during the molding process. If we take a very small molding machine, we make small elements, and we have normally a very small inlet system like this. And what happens in the molding process or after the molding process, you break off the inlet from the element, and then you grind this and reuse the material in the part. If you want to produce more, then you make bigger inlet systems like this. You can here make 8 elements at a time, which is of course 8 times bigger than using the small molding machine. But you have also a lot more material to recycle and reuse. So the material will be going through the molding process where it's melted, melted, and injected and cooled down. So this is a lot of thermal exposure to this material. But for real production, it's not the small ones. We are talking about inlets at this size. And here we have challenges both because it goes to the molding machine a lot more times because it's much bigger than the parts. And we do also because we are filling the inlet system very, very fast to make the polymer really flow easy. Then you have shear heats, meaning you have local heating at a very high temperatures in these systems. So that's 2 challenges. You have the repeated molding and you have the shear heat in the runner systems. And what can we see? An example is here that you have ABS. You have ABS which has been molded once and ABS which has been molded 10 times. And you can see it turns slightly yellow. And of course this is mainly an optical thing. And this is the material, but the colors can also degrade. And here we have an example where we by purpose have compared this color molded at the right temperature, 235 degrees, and then we have elevated the temperature to 275, 300 and 325 degrees, and you can see how different this color is. This is not just another color. And these temperatures are not unrealistic to reach in these big inlet systems. So we have both local heating due to the shear heat, and we have the repeated heating through the regrinding of the inlet systems. And that is why we are focusing on stabilizing the materials so they can be more robust. The same for the colors, that we select the right colors for the process, but also looking into the molding process and the runner systems so they are designed so they are not creating shear heat and a very low volume of material which needs to be regrinded. I hope that gave us flavor of the challenges. Thanks.
Right. So that was the first example of an actual product being recycled and what comes up as challenges there. And before I ask Søren some questions, I'll show just a different challenge that we have in Novo Nordisk to see how the different products are actually asking different questions. So I will immediately go to the next one here.
Hi everyone, and thank you Jacob for the introduction. My name is Jacob Moberg Sandager. I'm a senior material engineer here at Novo Nordisk, and today I want to go over and introduce why in Novo Nordisk we rely on different types of polymers to make our devices and why it's so critical. So the integrity and functionality of the device is heavily dependent on the different material choices you make during the development. Some examples of these materials are PP, polypropylene, polyamide, PC-ABS blends and stuff like that. And all these serve a unique function inside of our device to ensure the best experience for our patients. And to kind of illustrate this and help visualize a little for you, I have an exploded view here of our device. And essentially, so to start off with the PP, the polypropylene, we have the cap, the cartridge and the housing here. And the PP is quite nice because it's a very lightweight polymer. And also it's quite easily moldable, so it's easy to take the shape if you want more complex or small geometries. And while these parts are large in the context of our device, there's a lot of small features internally that you can't see in this image. that can be filled out with the PP. And also, as I mentioned, it's lightweight, and if we were to change to another polymer, we will see that the weight of the device increase significantly, which can have a negative impact on the patient's experience with the device, as our device is used for all types of people, not just a very specific demographic. Then we have pump. It's used in quite a lot of our materials. You see it in the piston rod, the dial, the spring base, etc. It's used in a lot of components, and that's because we use the pump when we need higher strength requirements for material, as pump is significantly stronger than polypropylene. So that allows us to have small thin wall designs that can fit inside the tight packaging of the housing, as everything is packed essentially inside the housing. The only thing outside this housing you basically see is a dial and push button, the cartridge and the cap. Everything else is squished in here. So that's why we need the pump, so we can make these thin walls parts that have a high strength and can handle requirements that will be exposed to the market. Another reason is also we rely on it for its friction properties, and it has a quite low frictional coefficient. If we had a higher friction coefficient polymer, it would actually have a significant negative impact on the dosing experience for the patient. Again, it would take much longer to inject the device actually. It would still be possible, it would take a lot longer, and that's not super comfortable having a needle stuck in you longer than necessary. Finally, we have, for example, the PCFS, as the last one I'll go over. It's on the push button, and here it gives some nice scratch resistance compared to the PP, for example, as the patient will be interacting with this surface the most and put the most force on this while using it. Another one is the scale drum down here, which has been optimized for laser engraving. We have different variants, it's a platform display touch device, and it'll be used for many different types of drug we serve on the market for different patients. So that will modify the laser engraving on here, so we don't need to redesign a whole new device whenever we have a new drug to serve our patients in that scenario. So that's very nice. And all these different materials are not one-to-one replaceable with each other. We need them to serve their function, and we do try to cut down as much in our production, and also in future designs we're trying to optimize our material choice as much as possible for recycling and durability. But in some cases it's simply not possible for fitting everything in such a small compact form factor with so much functionality. So therefore we need to make our sorting process more complex for recycling, and then we're working that with our take-back program. But it also means that because these polymers have different chemistries and compositions, we also need to understand how do they behave when they're exposed to degradation mechanisms such as thermal or UV degradation. And that's where the CFIT project is excellent, as the research has been done here to help us understand. Because if we can have this understanding, we can know how to do our material selection better and also optimize existing materials and production even more than we do today. Thank you.
Okay, great. So here we have two very different types of products and a set of challenges that go with each of them. But what really interests me, and I hope I can ask this question to both Søren and Jakob, but first maybe Søren, you talk a little bit about how you decided to look into stabilizers and stuff like that, but there must be a million things to try to look at when you want to optimize your recycling capabilities. And of course, we want more circularity, but what are the actual drivers for how to decide what to focus on?
Checking first the sound, is that okay?
Yeah.
Okay, fine. Yes, you're right. There's not only a billion, there's a million, there's a billion factors to look into it, because this is a full system, and it's really about understanding what are the actual causes for what we see. Is it the shear heat? Then we need to work with the runner system. We need to work with the moulding process. Is it the residence time in the screw or in the barrel? Then it's something else we need to focus on. Is it the stability of the pigments? Is it the compatibility between the pigment and resin? And it's a graduate optimization, and it's also you can say a battle between productivity, meaning how much can we get out, how fast can we produce, how many elements can we produce at a time. So it's a laws of physics meeting business and challenge each other. And there we sit in the middle to understand where do we adjust? Is it the material? Is it the process? Is it the design of the mold? Is it the design of the elements? Or it can also be auxiliary equipment. We have also seen in the past materials which are degrading in the drying process if we don't have standards on how long we can dry materials. And the CFIT has given us, you can say, more pieces to this understanding, which are actually helping us ahead and putting in the right solutions. And I showed an example of ABS, but we do have a multitude of materials, meaning we have a billion of opportunities to come to work.
That's great answer, Søren, because it is very complex. I might ask the same question to Jakob, but kind of like you presented here a question of all the different needed types of plastic that you have, which comes with another set of challenges. How do you decide to go further with research and understanding of a specific material? What is actually deciding factors?
Yeah. So in this case, it's honestly quite simple. The answer here is simply we chose our polypropylene because by volume, it is our most used material in our production. So that's where we see the biggest potential return. And also on top of that, polypropylene is a material that is being recycled in the industry today, not in the medical field, but other industries are using it. I've seen it in a cosmetic for soap bottles and different things, but also showing there is some potential there. Where if we see some other polymers like PCBS, that we are seeing people starting to recycle those, but it's not as common as of applications. So it's kind of been a combination of what we see as, I wouldn't say the low-hanging fruit, because it's still quite complicated, but also where we see the biggest potential return if we succeed with this. That is the simple answer, I would say. We would like to do it for all our polymers, but now it's just picking one because, similar as Søren said, if we take all of them at once, we will get overwhelmed because there are a billion different factors to look into. So we're trying to narrow into the one we think will have the most return and the biggest success. Yeah.
That makes a lot of sense. So there are, of course, drivers to look into parts of this. But I like that we start this session off with this industry perspective, because those drivers might not always be the same that we see in more basic research in universities. But there are luckily lots of good links also across these sectors, and that's also what we try to highlight here. So I think we will, in the interest of time, go to the first deep dive from a university perspective, where we try to go deep on a specific type of polymer and get some insights there. So the first up is Egede Daugaard, who is a full professor at DTU in the Department of Chemical and Biochemical Engineering. And he has recorded a very nice video that will take us through some interesting insights in polyamides and their recyclability challenges. So please ask questions in the Q&A if you have some while we're watching this video, and I'll try to ask them to Anders, who is also here.
Thank you for the introduction. Today I will be sharing a study about mechanical recycling of polyamide 66, which is one of the polymer systems that we have been looking at in the CFIT project. This specific study relates to the effects of combining different master batches with different base compounds and how this affects the recyclability. This study was conducted by postdoc Anna Rik in collaboration with my colleague Christopher Almblad from DTU Chemistry and myself from DTU Department of Chemical and Biochemical Engineering. So as a starting point, nylons, I'm sure most of you are aware, are used for a broad range of engineering applications, from fishing nets to gears, different types of knobs, generally high quality applications. So finding across the industry a lot of different applications. We use about 8 million tons annually, 1/3 is polyamide 6,6, which is the target in the study that I'm presenting for you here. The polyamide structure, as you can see in the slide, is built around an amide structure with different types of spacers. But for polyamide 6,6, that is a carbon spacer from a dicarboxylic acid and a diamine. That also means that we have heterofunctional atoms in the backbone. This may sound a bit complicated, but it is actually rather important, because that means that once we start heating these polymers in processing, a broad range of degradation phenomena will take place. These can be of more or of less importance to the recycling of these polymers. If, for instance, as we can see in the first reaction on the top, it's an abstraction of a proton that leads to a radical, and that can then lead to a subsequent range of other species being formed. The first reaction on its own is not necessarily a big problem. There are also antioxidants present that will suppress some of this degradation. But on the other hand, it will ultimately lead to formation of a broad range of different other compounds, which can definitely become a problem later on. If we look at these reactions on their own, they lead to chain scissoring and therefore loss of chain length. Chain length scales with the tensile strength of these systems, and therefore we would expect that we would see a loss of mechanical properties as chain cleavage takes place. However, once we have made these functional groups, we can also expect them to start reacting, and therefore we also in these systems expect the opposite reaction to take place, namely cross-linking, where we start to form networks or at least branch structures in this system as heat and temperature as well as processing and shear due to the processing is being applied to the polymer melt. A lot of things are done to suppress these things, and one of the most commonly used approach to this is that you use additives and stabilizers. So what you normally do in the industry is that you combine this nylon with master batches containing additives, antioxidants to protect the polymer, stabilizers for processing stabilization, flame retardants if necessary, UV stabilizers and other things. This master batch typically comes with a carrier matrix, which can be the same polymer as the one that we're using for the base resin, but it can also be other polymers. In addition to this, we also have pigments, different colors. There can also be fillers and other things in these systems. So generally in the industry, you would be combining a base resin that could come from a range of different suppliers with master batches that could also sometimes come from a number of different suppliers. These systems are optimized for the first and initial phase of the use, so the initial processing. And once we've mixed them together, it's not possible to get the low molecular weight compounds out and obtain the pure resin again. You will always have this mixture. And one of the problems here is that if there's any adverse combination of the additives or that comes from the base polymer or from the master batch, we would have a risk that we can have an acceleration of the phenomena happening in the system. And this is some of what we've observed for some of these systems. And there are not many studies on these combinations of additives. So this is actually a common way of operating in industry, that you would combine a different resin provider with a given master batch, under the assumption that this would actually not be important for the use of the material itself. The mechanical recycling in this case was done through an extrusion process, where you can see here that supplier 1 was run for 1 and 10 cycles. Then we combined supplier 1 with master batch 1 with master batch 2, and also ran them for 1 and 10 cycles. Similarly, for another supplier, we did exactly the same samples. Reprocessing, where this was cycled repeatedly through the process to obtain an extruded filament, which was pelletized and then used again and again. This allows us to get an insight into what happens in the recycling step. And as you can see here, there's a clear coloration happening through these recycling steps, even though it's only 10 cycles. It's very clear that the natural grade after 1 cycle compared to after 10 cycles does not look the same. This becomes even more pronounced when we look at the red dye, where we can see a very clear discoloration happening in the system. If we go at this in a little bit more academic fashion, we can actually measure on through color tests the impacts on lightness, on green and red color, blue and yellow color, where we can clearly see that between these different cycles, we do have a significant change in all the compounds. But what is maybe interesting here is also to notice that the suppliers don't change the same. So already from the supplier side, there is an effect on the different coloration, and we can see that this is not at all the same. If we then, on the other hand, look at these, which are the red colored samples, so you can see that it's supplier 1 combined with master batch 1, or supplier 1 combined with master batch 2. If we, on the other hand, look at the colored samples, where we can look at different combinations of suppliers and master batches, as you can see here, we see a similar trend where one combination with one master batch and another master batch does not lead to the same changes in coloration over time. So this is just a way where we can quantify these changes in color that you, for the red samples at least, easily could observe by the naked eye, but where smaller changes are maybe a bit harder to capture. But it's very clear to see that there are significant differences between the different combinations. If we, on the other hand, look a bit more at the melt flow properties of these systems, we noticed one thing in these samples that we did not expect, and that was that some of the samples, like the one you can see with the red arrow here, it changes its properties as we're measuring it. So we run rheology tests, in this case, a frequency sweep on the different compounds. We can also see that the different compounds react very, very differently to the systems. And what we're observing in this case for the red arrow is actually a cross-linking taking place for this specific combination of master batches and suppliers. So in this case, this is a 10 times recycled red sample that clearly shows a degree of cross-linking after reuse. What happens in these systems is actually that the system gets affected by the heat and exposure that we have in the rheometer, where we clearly see when we look at the samples that we have a cross-linking taking place on the outside of the sample. So this is very easy to observe on the samples, but it's also a very nice way to have something that's extremely sensitive to changes in the material, and therefore allows us to monitor what happens with the system over time. And if we then look at the rheology plots as storage moduli over versus time, we can see that for all of the samples, we see an increase in storage modulus as time goes on. That indicates that there's a reaction going on, the system changes. On the other hand, what we can also see is that after multiple recycling steps, the initial modulus is lower, which means that we have had some of this chain cleavage taking place in the samples. What we can also see is that once we measure on samples, particularly 10 times recycled samples, we see that for some of them, we actually get a severe cross-linking taking place inside the rheometer. So this very clearly shows that there is differences between the different systems, which relates to the supplier and the master batch combinations. We have also done tests, which I don't have the time to show, but actually to look at antioxidant properties to see if we can suppress that. So that is not possible. So this is directly a result of the formation of these different functional groups that I showed you in the first place. So this is just a little bit of insight into what is challenging in a recycling case. So for polyamide 6,6, it is feasible to recycle it also multiple times, but it is also challenging over time. And particularly when you start to consider coloration, choices of different master batches, the industrial angle on this becomes increasingly more complicated. And it's very clear to us that the choice of master batch influences the thermo-oxidative degradation. Rheology has been seen to be the most effective analytical tool to capture these differences, especially between different recycling sessions. But the take-home message from this is really that the plastic and master batch combinations should be designed for recyclability, and they're not today. And this is something where it is extremely important that there's a good link with the supplier and your choice of master batches, that these different combinations are actually tested, so that you don't just in the middle of a production decide to change for a different supplier and suddenly you will observe differences in this kind. And to us, this is actually a very interesting result because it directly pinpoints something where we really need to think differently about the plastic compounds that we use for recycling. I would like also in the end to acknowledge Trace through the CFIT project, which has supported the funding for doing these studies, among other studies.
Yeah, so thank you so much, Alice. That was really an interesting talk, and it's also clear that the direct mechanical recycling of polyamides, or PA66 here, has some limits, and that it is very clear that it does have an impact on what, of course, you put into the system. So I'll see if we have some questions already, which doesn't seem to be the case. But I would like to begin with to ask you as a researcher, do you think there should be industry-wide guidelines on what kind of additive compatibility you can have in when you combine some of these master batches with different suppliers? Or is that a way to go? Or what do you think actually is the way to go to make to reduce this problem?
I think it's a question of how we can see a setup. I think there's also a lot of discussions about how we deal with this also in other contexts. This whole concept that you don't necessarily, as a producer, know everything that is in your materials is problematic when we start looking at some of these effects. And therefore, it would be a huge advantage if that knowledge was transferred with the compound. So that it would be possible to actually look at this. The problem with this is that this is also part of the know-how in producing these materials, and therefore the producers of the raw materials have their know-how embedded in the material itself, and therefore some of their choices really affects these possibilities. So if they provide all of this information, then somebody else can just copy their compound, and therefore they basically could take themselves out of business in doing this. So I think it's a very delicate balance where we really need this information, and I think there are a number of solutions out there that's been proposed. So that could be a third party that has the knowledge and acts as a go-between who will then know when you start making these combinations that this is problematic. But I think in its essence, it's really about designing this not only for single use, but actually for multiple uses. Then this with the coloration is one aspect of this where we can't just choose freely. But I'm sure there are many other cases where we're also very interested in actually designing these compounds much, much better. And that's a journey that I see is only just starting. There are some companies who are moving towards this where they have a setup with the producer of the raw material, where someone in between sells the material to the final user, and they keep track of all the different aspects in that, and they will take it back, recycle it, and make sure that it's used in the right way. And then the only thing that remains unsolved in there is how should it be worth it for the original supplier of the material? So it should be worth it for everyone in the chain for this to actually happen in reality. And I think this is one of those that it would be very interesting to see how we can solve that. Because every time we recycle something, then someone is not selling new pristine compound. And if they are the ones deciding what is in that original compound, then it would also favor strongly how interested they are in making that better recyclable. So it's not a simple thing, but I think there's some transparency that we need, but it is really critical to these businesses and therefore difficult to obtain.
That makes a lot of sense. So once again, it's very complex and dependent on many things, and that's just the way it is. So we have a question or a comment from Jesper here that says time tests for PA will yield different results depending on how the test is conducted. So lack of oxygen between plates mean degradation differs from a test where oxygen is present. Yeah, do you have any thoughts on this comment?
No, I completely agree with Jesper. I'm not trying to claim that this is a way that we can observe something that is universally applicable. But if we do the test in the same way every time, it allows us to demonstrate a difference between the samples. So as long as the test is done in a reproducible manner, we should get the same results if the compounds are the same, and they're not. So in this way, we demonstrate a clear difference between them, and that was what we were looking for. We needed a way to investigate this where we're not looking at subtle differences, but where we actually get a very clear outcome from this. But of course, Jesper is completely right. Depending on the amount of oxygen that comes into contact with the sample, we will get different results from this. But since all the samples have been manufactured in the same way, same discs, same thickness, the protocol is exactly the same, we can at least compare between the samples. And I think that was the point we were trying to make here, that rheology as a whole is actually extremely sensitive to all the changes in the system, which I'm sure Jesper would also agree with me.
Very good, Anders. Thank you so much. We will, for now, move to the next part of the session, which is then changing material into ABS. So ABS, which Søren Kristiansen from Lego also talked about in the beginning, but now we will have some insights and perspectives from Associate Professor for a little while longer, Mogens Hinge from Aarhus University. Mogens will be a full professor at Aalborg University from November 1st. So final week of that role. But Mogens has been in this project and looked at ABS as one of the things. And we will show you here about the degradation of ABS in actual recycling processes. So degradation from different areas, also looking into exposure to light and heat. So I'll try to share this presentation in just a second.
Hello, welcome everybody. My name is Mogens Hinge, and I'm trying to shed a little light on the recycling potential of ABS plastics. I'll take a chemical approach in my explanation. So let's start out by defining, first of all, what is ABS plastics? I've taken some pictures of different things. So here is a casing for one of our equipments. This is the edge of my computer screen. Again, casings here for computer components and also the keypad for our security system here. So why is ABS chosen for these materials? The first reason is the impact resistance. So ABS has good impact resistance. It has a nice surface gloss, so you can see you get really wonderful surfaces. It is dimensionally stable, so it's having the same size day by day. Then other property is that it is creep resistant, it is abrasive resistant, so it doesn't scratch that easy. And then there are rigidity, good weldability, and insulating properties. But the main reason for choosing ABS is the impact resistance, the surface gloss, the high dimensionality, and the easy in processability. So let's dig a little bit deeper into what is ABS. So if we zoom in onto the material, then we'll see that ABS is not a homogeneous polymer, but it is a polymer blend. So that basically means that we have a base matrix here illustrated in light blue. And in the case here, it is a styrene acrylonitrile base that we have. And then in this base, we have islands or small lumps of polybutadiene. The polybutadiene works in a way that when you impact, for example, the ABS from below here, then the sand phase here will deform and then transfer the energy into the polybutadiene phase that will deform and convert the energy into heat. So in that way, the material do not shatter or break when it is subjected to an impact, but it simply just takes all the forces and divert them into the material, and then in each of these small lumps of polybutadiene, they will then convert it into heat. Now, if we dig a bit deeper into it, then the ABS is then a polymer that is constituted of 3 different monomer systems, or 3 different polymers. So you have the polystyrene here, which is the part of the sand phase, and that is taking care of gloss and about rigidity of the material, but also the processability. So having the styrene phase is beneficial for these properties. If you take the acrylonitrile phase, so here, which is also part of the blue matrix, then this is mainly giving the ABS material chemical and heat stability. So again, very stable base to have. And then the polybutadiene, so the orange parts over here, they are constitutive of two types. So the butadiene can be incorporated in two different ways. So 1,4 polybutadiene, where you have the double bond inside the backbone, or 1,2 polybutadiene, where the side group contains the double bond here. Now, this is making this rubbery phase, and thus is the impact strength giving a part of the material. Now, how do I know that this is what they're made of? For that, we need to use chemical and analytical techniques, and throughout this, I'll mainly use IR as my argumentation. So what did we do? We took 4 commercial vendors' plastics, all ABS, that should have approximately the same properties. And then these materials were subjected to an IR measurement, and therefore we have ABS1, which is vendor number 1, and that has an IR trace here. Then we have ABS2, which is vendor number 2, that will have a trace here, then version 3 and 4 down here. So in this way, we have the different vendors and named them ABS 1, 2, 3, and 4. I have also marked some blue squares here, which is sort of like where the interesting part goes on. So if we take the drawing from before, then I'll have some IR functional group indicators available. So first, we have the polystyrene. So this benzene ring that we have here, this aromatic system, will give peaks here just above 3,000, wave numbers of 3,000. Besides this, it also gives these peaks at 1,600, but also these 2 peaks down here at around 700 to 800 reciproc centimeters. So we use these for reference. So we always reference our relative amounts to polystyrene phase. Now, we also have the acrylonitrile. This group here has a very nice peak just here, as you can see across the different vendors. It's always there. And then we have the butadiene, and depending on how they're incorporated into the material, they will all both be present, but depending on how they're incorporated, then they will have peaks different places. So if we take the 1,2 butadiene, it normally has a peak here around 960 reciproc centimeters here. But if we then take the 1,4, then the double bond will have a higher energy level and therefore have a band around the 910. So in this way, we actually have here a very clear indication that we have both of these in all of the materials, which is very common. They are random distributed in the material. Okay, so what is the main driver for recyclability of a material? And that is, of course, material degradation. So in this project, we have been working on degradation at 3 different levels. So the first level is mechanical degradation. Here, strain is our main driver for the degradation. The strain or the stress also for the material is pulling the material apart, and when it pulls it apart, then you can break the bondage. This is normally seen in injection molding, in extrusion, in chopping, all processes that is used to reprocess the material. I've taken the different vendors here. So here is how we receive it, so the virgin version. And then we have recycled it in an injection molding, chopping, injection molding, chopping cycle. And we've done that 10 times. And it's clear to see that there is a color difference between the different samples here based on this. I'll return to that a bit later. A second degradation of things that we normally see is UV or irradiation in general. And that's because all the products are used in real life. So it could be a part of a car, or it could be something you have in your window shelf standing around, or it could be my computer screen here that will be exposed to sunlight. So UV exposure from sunlight is the main degradation mechanism that we see in normal behavior. So window shelf, where it's behind glass, but it could also be garden tools that are standing outside in the garden getting UV irradiated. We have the ABS1 here, and we have irradiated for 20 weeks. So here's week 1, 5, 10, 15, and 20. And I think, again, it's easy to see that we have a color change across the course of time here. Then the third approach that we would like to look into is thermal. So that's basically heat, when things are heating the material. And now you could wonder, where do we find heat in our everyday life? But hot cars is a very classical example. So it can be very hot inside a car during summer if it stands still in a hot day. Dishwashers, when you wash items, then normally you have 70, 80, 90 degrees in the dishwasher in order to make sure that it's clean and antibacterial. But also other things that we don't think about. So here I'm just taking the example of a shipping container. So we make a product and then we need to ship it to a certain country. And then when it passes equator, it will be standing on a boat, the sun will be shining, and that means that there can be an enormous temperature inside a shipping container or when it stands on a wharf waiting for the boat to arrive. So these are the three degradation mechanisms or degradation approaches that we will look into. So mechanical, UV exposure, and thermal. Again, we have taken here a picture of some of the pellets that we cut open. And then we have again exposed it to heat for 20 weeks. And in this case, it's at 120 degrees for 20 weeks. So week 5, 10, 15, and 20 is shown here. But let's dig a bit more into how does the chemistry change when we are subjecting them for these kind of degradation approaches. So let's start out with the mechanical. It's very obvious that you have a color change. So something has happened. That is not up for discussion. Now, when we start to look at it chemically by the IR, then the first thing we see is that we compare here the 10 cycles and then the no cycle or 1 cycle because it's produced in the same way. So the 10 cycle and 1 cycle, if you compare those, then here on the styrene thing, we don't see a lot of change. We don't see it here. We don't see it here. So basically, we can safely conclude that the styrene phase seems to be withstanding at least the mechanical degradation. Again, if you take number 2, then these pairs are also not changed. These are not changed. These are not changed. So in that way, the spectrals are the same, and thus we don't see any change. The same if we go for the acrylonitrile, the second parameter we had to look into, then we see this peak again. If we compare them pair by pair, we don't see any change as we go down. That doesn't change, no change, no change, and no change. Now, if we go to the butadiene phase, then you might argue that, hey, this seems to be a little bit smaller than this one, so that might be just a small change. I know that we have to be a bit picky here and be very strict on it, but it does look like there seemed to be a tiny change by recycling it 10 times. Again, if we compare the pairs down here, you might see the same here. You might also see it, and down here again, you see it. So there might be a tiny, tiny change in the butadiene phase due to mechanical degradation. However, I think it's pretty safe to conclude that there's almost no chemical changes going on. And that means that we have almost no degradation due to reprocessing of the material. Let's move on to the next one, UV. And here again, we have irradiated these for 20 weeks. But please remember that these have been irradiated intensively for 20 weeks. So that means that it's no day or night. So if you take into account that the sun is not shining at night, at least here in Denmark, then this 20 weeks is equivalent to 13 years of UV exposure outside here in our parking lot. So just be aware that when I talk about 20 weeks, it's an accelerated test, which is corresponding to 13 years. The first thing we observed is that the 1,2 pp phase was simply not detectable after a week. So after we have irradiated this constantly for a week, then this is completely removed. We cannot see, there is no peak, it's gone. And if we look at the ratio between the styrene peak that I told before, around 700 respox centimeters, and then the peak for the 1,4 butadiene, what we see is we see a dramatic reduction already within the first week. And then we see a slow reduction. And then after like 3 weeks of constant exposure, we start to see that there's not really anything. So that basically means that when we irradiate it, it degrades extremely fast. Now, there is actually a catch to this story. So before we just conclude that this is extremely fast degrading, then we have to look into the IR method a little bit. So here I try to illustrate what goes on in the IR. So we have the polymer sample. The blue indicates the degraded part of the polymer. Then we irradiate with IR light into the sample. It reflects on the surface here, and then it sends evanescent waves into the material. Now, these evanescent waves are only sent approximately 3, 5, 6, so a few micrometers into the material. When they do that, light is lost, and then we look at the other end of this. We look which frequencies do we miss, and that is what gives us the IR spectrum. But what I'm trying to say is that you irradiate on the top here. If you turn these around, then even after 20 weeks, or at least definitely after 5, then the backside is not affected because this method is a line of sight method. And that basically means that we relatively fast will lose our signal, even though that you have fresh and virgin material on the backside of this. Then whenever the first few micrometers are broken, then you start to see a disappearing of the signal. Now, let's look into the thermal. And the thermal, I showed you this picture where we have the thermal material. So we have the white material. Remember that the material was right in the start. And then after 5 weeks at 120 degrees, we start to see this yellowish or orange, brownish shell around it. After 10 weeks, we start to see even more and more. So by simply looking at the amount of white in each of these pixels, making the relative to the surface, then we can actually get our first indication that something is going on. So just looking at the color alone and seeing this ratio, we actually see that we have a very nice degradation as function of time here. So over the course of 20 weeks, we actually degrade the material and return all the way down here where it's almost only brown. There are a bit of difference between vendors, and that could be due to different amounts and different types of additive or different type of targeting properties. So it could be that you have maybe here vendor number 3, that they have added a bit more antioxidant or other additive to it that will ensure that it maintains more or less the same, but then when it's consumed, then it also just degrades. So in this way, we're just shifting the time escape a little bit. But let's look into the IR. So when we look into the IR, what we see here is that we have, of course, a lag phase, maybe of a week in that range. And then again, we see a dramatic drop in the 1,2 butadiene phase. It completely disappears. So the dangling chains disappears fast. And then the 1,4 disappears and seems to end at a constant level after a while. So again, here we see that the degradation is sort of like complete within like 7 to 10 weeks. And that's also followed by this. So after 7 to 10 weeks of 120 degrees exposure, then we start to see that we end up at a constant value. So let's go back and then say, okay, what is then the recycling potential of ABS? And I think we should consider the use case. So where are we talking about the potential? So if we start looking at the mechanical reprocessing, that means that if a company is processing ABS, then the scrap or the runners and spurs and stuff like that, that can easily be regrind and reused. It doesn't seem to degrade the material significantly. There might be a color change, but if you're dyeing it heavily in any color, it could be black or whatever for a car, then that doesn't really matter. So we don't see a lot. But we also could imagine the situation where the scrap cannot be reused internally in the same factory, but can be shipped to another factory, can then use it. And again, same story, it does seem like we can easily do this. So at least with 10 cycles, we don't see a lot of degradation of properties. Now, the second thing is if you have a factory manufacturing a product and send it out to consumers, you, me, and everybody, then we use it for a while and we will expose it to heat and we'll expose it to UV and all of these things for a longer time than you do when you reprocess it in your facility. So that basically means that here you will have a lot of degradation. Then we return it to some sort of recycling facility. They can maybe sort out or they can extract the ABS and send it back to the factory. Now, this is pretty challenging because as I have shown, the butadiene phase is actually disappearing. It's getting destroyed. So it's gone. And the butadiene phase was actually the part of the material that makes sure that it had the high impact resistance. So now that you remove that, then you get a more brittle material, and that might not be acceptable when you return it to the factory that is producing the product. And that means that basically you can't really recycle it, or at least you cannot make primary recycling, and you might need to recycle into a lower quality product that do not have the same kind of impact demands as the original products was intended. So it is definitely challenging because the butadiene phase is disappearing. I hope that this gave you a good introduction and a good understanding of the potential and where is the challenges in recycling ABS plastics. Thank you very much for your attention.
Okay, thank you, Mogens, for a very nice walk through the ABS and different degradation mechanisms, and good points on that. So a quick question from me would be, if you look into the research on degradation of ABS, what would be the most important research to continue into and delve into at this point in time, at least from your perspective?
So I think at the current time, there is an okay understanding of how the how the degradation mechanisms are and how it's all right destroys and is sensitive to different kind of external exposures. But I think when you're talking about recycling, the largest challenge is that you have a chemical change of the material that is not easily reverted back. So generating the double bonds demands very harsh chemistry that will then just destroy the material completely. So the question is if it's possible to exchange the butadiene phase, maybe add more butadiene in a secondary process, or maybe extract the other components and then add in a new butadiene phase. But from an impact point of view, then the butadiene is crucial. So you need to have it. You cannot just say, okay, it's gone, but you need to have it, or else you start to see embrittlement. So I think that the challenge there is that the material itself, part of that, a central part of that, is destroyed. It's broken down. Yeah.
That makes sense. So I think I received a comment here. So a question is, have you looked into any ways of repairing or slowing down any of these degradation mechanisms in your research?
No, not currently. I think all the classical methods are still valid. So antioxidants, radical scavengers, these kind of things. So in general, what can I say? The strength or the safety of the polybutadiene phase is actually governed from the additive that is added to the product. Because if you don't add any additive, it will also be destroyed much faster. So I think that the additives and the combination of additives is sort of like the thing that saves the butadiene phase.
Oh, so we have a question directly from Søren.
Cool.
That's more and also kind of a supplement to what Mogens told, because what is at least what we have been struggling with or been investigating to actually together with universities and Mogens is also in another context the colorants used for ABS, because there can be degradation mechanisms triggered by use of wrong pigments, and that you see over years, and you really need to understand these mechanisms. So that's at least an area we are looking into.
Well, very interesting discussion, and I think we will continue that with the panel later, maybe. And for now, we will go to the final presentation of this part of the session, which is from Jesper de Claville Christiansen, who is a full professor at University of Aalborg at the Department of Materials and Production. He will go into another kind of plastic, which is PP or polypropylene, and talk about the understanding the relationship between structure and function, and looking into possibilities to recycle this material, both chemically and mechanically. So I will share his presentation shortly.
A lot of the polypropylene that we face when recycling is post-consumer grades. So it's often mixed waste and heavily degraded, polluted by various stuff. And in these cases, chemical recycling would be a very attractive process. However, it's also very energy requiring, so whenever possible, it would be extremely good if we can mechanically recycle polypropylene. So typically, it would be when you have a very clean and large quantities in a waste stream, or if you have in-house waste from sprues and inlets from injection molding, for example. Polypropylene is a very common material. 20% of all materials in the world are estimated to be polypropylene. It is a cheap material with good mechanical properties and also resistant to temperature. You can do mechanical recycling or chemical recycling. One of the problems by doing mechanical recycling is that polypropylene comes in many grades with different colors and different additives, which makes sorting very difficult and can affect properties, because a red polypropylene do not have the same mechanical properties as a green polypropylene because the pigments affect the properties. So if you collect polypropylene, you will have contamination with other polymers, could be a risk, but also different grades of polypropylene. Furthermore, for each cycle that you recycle polypropylene, you will have a degradation that will change properties and discolor the material. So, as a rule of thumb, mechanical recycling is a very nice technique for recycling polypropylene if you have a clean waste stream and if you have sufficient amount. And you will typically have this in your own production waste. Chemical recycling of polypropylene is yet not so mature, but it is very attractive, but it's also very energy demanding. But in a future where we have more energy available and the cost thus means less, the chemical recycling would be a very attractive way of recycling polypropylene. But for now, mechanical recycling is the most realistic way. When we recycle a polypropylene, we affect the structure. What happens with the polypropylene is that you cut the chains. So the thermal stress causes a bond to break, and then you have a free radical that will react with typically one of the antioxidants or the stabilizers. If you have IR spectroscopy, there are some bands that are sensitive to degradation. So you can get a measure of the degradation by using spectroscopy. One of the main effects when you get these shorter chains is that the movement gets faster. So Duchenne got the Nobel Prize many years ago, where he proposed that polymer molecules moves inside a network like a snake in a tube. So Duchenne introduced something called the reptation time. And the reptation time is the time it takes for this blue chain that you see on the right-hand slide to move out of the yellow tube. And when we degrade and recycle polypropylene, this movement and this time becomes faster. The reptation time is proportional to the cube of the molecular weight. This means that if a chain breaks into two equal parts, they move 8 times faster. There's also a relationship between the data we can measure in rheometry, where we can estimate the reptation time from the plateau modulus divided by the zero shear viscosity. So opposite our clean room, we have a temperature control room for mechanical testing. So what you see here is a tensile testing machine where we can place a sample between two holders and we can perform a tensile testing. When we do the mechanical test, typically what people do are short-term tests. So you place the sample here, a dog bone, and you pull it over and you measure the tensile strength of the material. This is, however, not always the best test to tell something about the material and the structure, because some mechanisms happens on short scale, time-wise, and other mechanisms happen at long scale range. So if you do tests like relaxation and creep test, it's very time consuming, but you measure something else in the material structure than what you do in a short-term test. So viscoplasticity and the effect of time on materials are very, very dependent on the structure, and variation in crystalline size and so on, you might not capture in a short-term test, but it would be very visible in a long-term creep test, for example. Polypropylene is a semi-crystalline material. So it means that you have both amorphous regions and you have crystalline areas. So if you look at the picture here on the left-hand side, you can see these crystalline regions shown as folded chains. So it takes time for chains to fold and to crystallize. And the more degraded the polypropylene is, the faster the movements and the faster the crystallization. So when you look at this sketch on the left-hand side, you can see that between these folded regions, the crystalline regions, we have some amorphous areas. And the mechanical properties are determined by the relationship between these crystalline regions and the amorphous areas. On the right-hand side, I've made a picture in a microscope of such a cut in a spheroslide. And you can see the structure very, very clearly. The structure determines the mechanical properties. So you can see on the right-hand side that you have chains that entangle. And if you pull these chains very fast, they cannot disentangle and you have some strength in the network. If you pull them slowly, they can move, rotate with respect to each other, and chains will slide. So in most mechanical tests that you typically see performed, they are short-term tests, for instance, tensile bars. And here the properties will be determined by this entanglement and by the crystalline structure. So there's not sufficient time for these amorphous areas to unentangle. So you get the properties that are mainly determined by the shape and size of the crystallites. The entanglement, you really have to have a low molecular weight before you do not have many entanglements. Commercially available polymers have between 200 to 1000 entanglements, and normally you would say that if you have like 7 entanglements, you start to gain maximum mechanical strength. So here are some results from real life. On the left-hand side, you have a polypropylene that have been injection molded once, and on the right-hand side, it has been injection molded 10 times. And it might be difficult to see the actual values on these slides because the numbers are very small, but the yield strength, the top point of the two curves, are more or less the same. So it means that the tensile strength is not reduced in polypropylene after 10 times injection molding. What is different is the elongation to break. So again, it can be hard to see the scale bar, but actually the 10 times injection molded has an elongation to break around 150, whereas the one-time injection molded have a elongation to break around 500-600. Is this important? Not really, because if you design a product, you don't normally design it to be able to sustain an extension at break this much. You design the product not to fail. So more or less, they are very, very similar. There are slight deviations, however, if you look at the top point in the softness just before the yield point. But again, designing a polymer, you do not design it for failure, you design it to not fail. So more or less, you can be happy with the mechanical properties of recycled polypropylene if you experience a short-term load. There are other types of load, like creep. And in creep, we have time dependency. And here suddenly the deformation is not in the lamella in the crystalline regions, but it is between the lamellas in the polymer chains. And this is where it gets important that we have a scission of chains, that they get shorter, and the time scales as well get shorter, because now suddenly the chains are more free to move around. And furthermore, what we observe when we recycle the polypropylene, if you look at the left-hand side, you can see that the crystallites are not even in size. We start to get variations in size, but also on the right-hand side in non-polarized optical microscopy, you can see that there are also interfaces between crystallites. So the morphology of the material changes when you recycle it, and it has some impacts. So what you see on this slide is a creep test where we have strain on the second axis and we have time on the first axis. And what you can see is the blue line where you have the virgin material, and the orange-red lines where you have 10 times recycled material. And the scale bar is logarithmic on the time axis, which means that you have onset to phase 3 creep, where you start to get damage in the material, almost a factor 2 in difference between the recycled and the virgin polypropylene. So for creep behavior, creep loaded samples, it is important to acknowledge that recycled material do not have the same mechanical properties. We are now in the rheology lab. Polypropylene can be in a solid state or it can be in a liquid state. If you melt the polypropylene, then you have something where the behavior is dominated by the chains. So different molecular weights, different additives, and so on are what gives the response of the melt. So performing experiments on the melt state actually allows us to see into the material to understand what is the molecular weight distribution, are there any interaction, what is the mesh size, so we can gain a lot of very interesting information about the chemical nature of our materials by rheometry. However, when you're in the solid state, you get large-scale structures like crystallites and other interactions, so this is not present when we study materials in the melt state. What you see here is an oscillatory rheometer. So what does it do? We can have different measuring geometries. What you see here is a lower plate, and you can see an upper cone. And what we can do is that we can lower the upper plate down to the lower plate, and then we can perform either a rotation or we can make an oscillation. So let's look at some rheological data. What we see here is the complex viscosity as function of frequency. So the blue curve, that is the virgin material, and the red curve, that is the 15-time recycled material. And we can see due to the chain cutting that we have a lowering of the viscosity by almost a decade, which is quite significant and very important if you want to process these materials, that they get very, very thin, so that can inhibit quite many processes. If we do oscillatory measurements and plot it in a little bit different way, where we plot the elastic response versus the viscous response, the loss modulus T double prime, that is the green curve, and the blue, that is the storage modulus G prime. Then you can see on the left-hand side a virgin material, and you can see a crossover point on this curve. This crossover point disappears when it's 15th time recycled on the right-hand side. And that means that the molecular weight distribution has been broader on one hand, but it also means that you have a shortening, a lower molecular weight distribution. If we try to mix stuff, this is my granddaughter mixing, and here I'm mixing, then we get these results. So you have shear rate on the first axis and you have viscosity on the second axis. And in this case, it's no longer the complex viscosity from oscillatory measurements, it's real shear rate measured in rotation. And what we can see is that the virgin material, the blue in the top, and we can see the 100% recycled mix in the lowest of the four graphs. So adding up to 50% recycled do change the viscosity, however, not as significantly as 100% recycled material. The reason for this is because the viscosity scales with the molecular weight in 3.4. So having the large molecular weight fractions significantly alter the viscosity of the sample. Many times the so-called Cox-Mertz rule, where you measure viscosity in oscillation and assume that the complex viscosity is similar to the shear viscosity, and that instead of the shear rate, you can plot the frequency in radian per second. It's a very, very common assumption, but I've done it here for these measurements on the polypropylene, and you can see that the curves do not coincide. So the conclusion is that Cox-Mertz rule is not valid, but it gives the same Newtonian viscosity, the viscosity at very low shear rates. You can also see that the shear thinning effect is much stronger in the real shear data than in the oscillatory data, which can be expected from the orientation of the change at higher deformation rates. One thing we would love to understand more in details is what happens to the crystalline structure in the material. In this lab, we have tried to do atomic force microscopy on some of the crystallites, and we have also been able to use MAX 4 for some image analysis on the polypropylenes. But this work is still in an initial phase, and we hope to be able to continue this in another project. In a research project like the one we have had here in CFIT, we are able to answer a lot of questions. However, for every answer we get, I think we get 2 questions. And what we see here is our scanning tunneling electron microscope. And this, together with other techniques, are available for more detailed study on atomic level, what is really going on. So even though we think that we have some answers, I assure you that we have many more questions that remains.
Very good. Thank you very much, Jesper. I hope you're also here still.
I am.
Perfect. So that was certainly a very nice deep dive into the world of rheology and polypropylene, and a lab tour at the same time, which was very nice. I'd like
I
to
think
get
if
in.
I can add
Yeah.
one comment to it,
Yeah.
then I think that it is very important to acknowledge that that we have chemical changes in the material, but we also have morphological changes in the material. And I think this is the major takeout for the polypropylene. And actually, I was burning to tell Mogens the same, that we have made studies on the ABS, where we have seen agglomeration of the butadiene phase that also changes properties. So even if we could see no change in spectroscopy, we could actually see change due to morphology. So I think that's one takeout of this presentation.
I agree. That's very interesting. Yes. So, and I guess you would expect that also. So there are also limits to mechanical recycling, right? So I'd like to. You also mentioned this point a little bit in your presentation, that if we zoom out a little bit, in your view, if we have very high energy requirements and cost for chemical recycling, do you think in the future that will be realistic to go that way to avoid some of these maybe morphological changes or all of the things that you have from degradation and recycling again and again? Or is
I
it still a last resort?
Lego made a very nice presentation up here in Aalborg once, where they showed that the biomaterials are never going to work, because the annual growth in biomass is 1 exojoule, and the consumption in 2050 of polymer material is about the same size. So we need to use either oil or to recycle plastics. And if we don't want to drown in oil or polluted material, then we have to recycle. So it's not an option to avoid recycling. I think the takeout is that we need to mechanical recycle. We need to use materials smart. So I think the whole supply chain on how we maybe have digital product passports, that we have traceability, that we know which materials we are using and can make a smart gathering and reuse of the materials. That is important. And yes, we will have a downgrade, but if we can continue to use materials to the highest value, I think mechanical recycling will be a very attractive way also for the time ahead.
Yes, very good comment, I think. So we got a comment from, or a question from Christopher Almdal. So he asks, I think you're running your steady shear experiments on PP mills too high a shear rate. The slope of your logarithmic viscosity versus shear rate is below -1. That indicates that you have not simple flow in your instrument. Do you have comments on that? A very technical question.
The terminal values of the shear test can be discussed, of course, because you might have edge fracture or slip or other effects, and it's fully correct.
Perfect. Well, thank you, Jesper, for a deep dive into PP. We will now open the debate a little bit. We don't have too much time, but I hope you were able to stay here just a little while longer for a discussion from the presenters of this session, where we have had a deep dive. And I think my colleague is trying to put you on the spotlight here so that we can see all of you. Let's see. And maybe I should just open up the discussion and try to, you should of course just raise your hand if you have comments directly to some of the questions. But I will start out by asking, so you also opened up that, Jesper, but so maybe start with you. There are so many new questions emerging every time you open up one box and look at that. What should direct the right questions to ask scientifically? Should it be directed by current needs or future needs, or what should actually help guide the research into specific materials, in your view?
I think Søren Kristiansen answered that question quite accurate, because he said that what it is all about at LEGO is to understand the basic mechanisms in the material. And I think if you understand these, then it's much easier to not run for testing this and that, because you already know that there is a thermal degradation. You can use a model to predict the amount of thermal degradation if it's this mechanism that is present. If you know that, I mean, so knowledge about what's really going on, the mechanisms in the material, I think is essential, because then you have a toolbox to answer all kind of other questions without the need for testing every time.
Yeah, so basic understanding of materials is essential.
At least that's my bit on it.
Yeah. Any comments to that in the panel? Yeah, Mogens?
I fully support both Søren and Jesper on this point of view, because I don't think there is any previous and future challenges. If we start to understand what's going on and we can start to circumpass these challenges that from this understanding, then I think that is the same solution to both the current and the future problems. And also, you have to remember that the polymer is just one part of a very complex system that can sometimes contain up to 10, 15, 20 different components. And it's the interplay between all components that we need to understand. So it's not an easy thing to answer. As Jesper says, there's a long way to go.
Yeah, so maybe a comment from the product side of things. Maybe you, Jakob, I wanted to ask. So one thing is understanding all these underlying challenges and understanding the materials, but there's also how you should balance your ambition for what tolerances you can have in your product. Do you think managing those expectations is also helpful in the whole scope of things when you obviously get some degradation or problems when recycling? Are from a product side, are the tolerances too tight, tolerance windows to actually do more recycling? Or do you have any comments on that?
No, it's just, okay. First, no, it's a good question. It's a little tricky to answer because it also depends on how you define your tolerances. Like, what is your, because again, that's also what I mentioned in the video. It depends on what the critical aspect of that material is. Because some aspects are very much impacted. For example, as Jesper showed, the creep is significantly impacted by the recycling process, whereas the tensile properties aren't that impacted. So I would say it goes back to, and that's why I also say we do component testing. It goes back to what application you're looking at, and then design around that if it needs a redesign, or maybe you have an application where the degradation mechanisms we're seeing doesn't actually impact your application specifically. So again, it goes back to needing to get this basic understanding out and mechanism understanding, so you know what products today are suitable for recycling, and where do we need to think differently or design differently around it. Because also based on some of the data that's shown here today, there are components and otherwise we wouldn't touch with recycling, where others, they could probably handle 100% and it wouldn't be an issue. So it's not easy to give a strict answer, because I wouldn't say we should, again, we definitely wouldn't open our tolerances. It's more understanding where is it suitable for our tolerances. Because people, at least the way I see a lot of discussions, also of our internal teams, is people have this idea of there's degradation happening, so that means everything is worse, and that's clearly not true.
Yeah, makes sense. Any comments to that? So, yeah, I think that pretty much sums up lots of the discussion here. So of course you need all of this different, the tolerances or the properties that you need are of course very much dependent on the application. That's of course clear, but it's also clear that this degradation, we are always looking at or trying to aim very high. So saying that we should try to recycle all of it. So I wanted to ask the question, you could clearly see in Jesper's presentation that there were some critical points where you add a little bit more material than you that actually has a tipping point, that at some point if you only add 10% recycled material you don't have a problem, and maybe also 30% or 40%, but sometimes there are tipping points, right, that now it becomes too big of a problem. And if you also look in that you want to recycle it multiple times, then there must be some sweet spots or at least some optimizations on specific products. So I think about you, Søren, and your ABS presentation, that obviously you can't have Legos that are falling apart because it's the 10th time that you have recycled the same material. Are you looking into that kind of balance in your work?
Yes, that's key for us to look into that balance, and all the Mogens mentioned the acceleration on exposure, but we also have to remember that the moulding process is also a huge acceleration of aging. I don't have the number, but I would assume that the these 5 minutes is equivalent to years of use in normal environment. So having long-lived products, this is a crucial phase to take care of. Luckily, even though the butadiene is the most sensitive part, ABS is super robust in many ways, but we have found by both studies, but also by all the years we have been using ABS, we have found the limit on at least good limits on where how far can we take it, how much can we reuse it, and when do we need to scrap the material.
Makes sense. Yeah. Yeah, so there are, of course, lots of things. Yes, Mogens, you have a question or a comment?
Yeah, I more have a comment than a question or an answer. We have to consider the fact that each product has different demands, and it has different tolerances, and it has different how far can it go before it's degraded, and all of these things. So I think that the simple question is saying, is there a limit? Of course there's a limit. Of course there's a tipping point. Of course there is something. But I don't think there is one number for that. I think that number depends highly on material, composition of material, but also how to process it, and finally, where is it used? Because it might be that Jakob needs to have very high purity of PP when he makes his insulin pens because it is used in a medical setting, whereas you do not have the same demand for high purity PP in traffic cones. So in that way, in traffic cones, you can sort of like just do and do and do and do, and you can see it degrade. Whereas in the other case with the Novo Nordisk pen, you can't just fill it in and see it degrade, as time goes. So I think that the question needs to be considering the boundary conditions around the product, the material, and the process. I don't think there is a universal number that gives us everything. It's not like, just do 75.3%, you're home free in all situations. That's just a ridiculous answer. That doesn't exist. So more comment on the complexity rather than, it's an easy question to ask, but it's very, very difficult to answer without any context.
Yeah,
cool.
Totally agree. And Jesper, your comment?
It is just to support my future colleague. Congratulations, Mogens. We're looking forward to seeing you here. The focus is very much on the product and properties, and this might be totally wrong. If you take the polypropylene, where we have a decade change in viscosity, if you have a production, a mass production where you have a lot of samples in a mold, you have a balanced runner system, and imagine just the viscosity change by a factor 2, then these molds can't be used anymore because you simply will have an uneven mold filling. So even if properties of the component is fine, or it might not be good for the process. So Mogens' idea about looking at the system, the process included, I think is very, very valid.
Yeah, so I think that sums up a lot of the discussion going on, and is why CFIT project is very both difficult at one hand because we're trying to look at all kinds of different things at the same time, and important on the other hand because you need to try to put together some of the different pieces of the puzzle. And that, I think, has been a burning question all the way through this project. And finally, maybe just asking one of you, this way of collaborating then between very different types of, we have companies that have very different problems in their production. We have university researchers with very different focus. Is this the way to move forward on some of these questions? What do you think, Anders?
Could you repeat that, Jacob?
Yeah, what do you think it's, how do we make the right type of collaboration to try to look at the entire picture, but then again, go deep where it matters? Is that trying to bring together all these different stakeholders in a project, or how should we approach it?
I think it's a lot of different approaches, Jacob, that you need to think about a lot of different aspects in this, and it's not a simple thing where you can just cut out part of the process. So ideally, you should talk to the people who produce the original compound. You should talk about the people who add the additives. You should talk about with the people who process it in the industry, and you should cover all the different aspects of the transition all the way through in order to approach this. That doesn't mean that there's not simple things that you can do along the ways of that process. You should also remember that we often talk about closing the loop, doing this hundreds of times in sequence. I mean, there's a lot of things here that it makes sense to do, and we should definitely do. But that doesn't mean that the material doesn't change. But the better we know the material, the easier it is to think this into the processes and actually take care of this. But it is just more complex. So we just have to respect the complexity and then take that into account in all the different stages in the process. Completely agreeing with Jesper and Mogens in that it's not just the material, it's also not just the process, it's also not just sourcing, it's everything. So there's no free meal, but you can definitely do some of the things where you bring it parts of the way. So yeah. Not really an answer, but more an underlining that it is complex.
Yeah, Mogens, a final comment on that?
Yeah, I'll just put a final comment on it, because we have now for decades and decades and thousands of years done research in each of our little tiny cubicles, and that have brought us so far. But I don't see a possibility of doing any kind of research from now on where you do not include where it's used, where it's come from, and these kind of things. I think that would be a silly approach. So my only comment to your question is there any other way? You know, I don't think there's any. I think that it's very important that we have Søren and Jakob, Frode, and these guys sitting there saying, yeah, but you haven't thought about legislation. And no, I have not thought about legislation. My world is very tiny. It's I have shown you how I see it through IR as an example. So we need each other. We need each other, or else we'll never solve this. It's too complex for one to carry. So of course we should work together, all of us.
This is very new to me. I didn't know there was a life outside my labs.
Yeah, I know.
I think that's a very nice way to end up with. Yeah, we need each other. We need to work together to move forward, and the world is very complex. So what should we do? That depends as the answer, and of course that's as frustrating as it is inspiring that we have so much to learn still. So thank you all for joining our session, and I think we can close the material session for now, and then Line will just very briefly talk about the next one. Thank you.
Yes, thank you all that has been in the sessions. I think it has been really great. I think we have come around a lot. And today it has been highlighted that it is very complex, circularity of plastic. And for the next time, we have the 4th of November. We will look more into, can we say, do we have some tools where we can help each other to figure out what is the right scenario? How do we choose the right circularity for each? It could be material, it could be something else, but how do we ensure that when we choose something, we choose it right? And also looking more about the material flow. So how do we actually get the material back, and how do we collaborate in the value chain, because if you don't, you cannot be circular alone. You need to collaborate with your stakeholders and throughout the value chain to get it circular. So that will be more the focus in the next CFIT webinar day. Yeah. But with that, I think I will end up the day today, and I hope you have enjoyed. Have a nice weekend when you come to that. So see you 4th of November.